In this video, we'll discuss converting equations between rectangular and polar coordinates. The graphs that we have studied so far have used rectangular coordinates. An equation where x and y are the variables is called a rectangular equation, but an equation where r and theta are the variables are called polar equations. And this is some examples of what polar equations look like. R equals 3 sine of theta, R equals 2 plus cosine of theta, R equals just theta. Typically in polar coordinates, the R is solved for, just like in rectangular, typically the Y is solved for. So let's transform the equation x plus 5y equals 8 from rectangular coordinates to polar coordinates. Now, remember our properties, our relationships that we used to convert back and forth before. We have that x is equal to r cosine theta, y equals r sine of theta, r squared equals x squared plus y squared, and lastly, tangent of theta is equal to y over x. All right, so we're going from rectangular to polar. That means we want to get rid of the x and y and replace it with something containing an r and a theta. Well, we know that x is equal to r times cosine of theta, so let's just replace it. R cosine of theta, and then plus 5y, y is equal to r sine of theta, so this becomes 5r sine of theta equal to 8. So technically now it's transformed from rectangular to polar, but we want to solve for r when we're writing a polar equation. On the left-hand side, we have a common factor of r that we can factor out, leaving us with cosine of theta plus 5 sine of theta equal to 8. And then all we need to do is divide both sides by that cosine plus 5 sine. And we get r to be equal to 8 divided by cosine of theta plus 5 sine of theta. And that's it. Let's transform the equation x squared plus 6y from rectangular to polar. Again, we're going to replace x with r cosine theta and y with r sine theta. We've technically transformed it, but we want to get it in the correct form, which is solved for r. So we have this squared, so I'll apply that to everything inside. We get r squared times cosine squared equals 6r sine of theta. R is the variable we're solving for, so really that's all we're looking at. And we have r squared and r to the first. This is quadratic in form. So let's get all of our terms on one side and try to factor it. R squared times cosine squared minus 6r sine of theta. We have a common factor of r that can be factored out, leaving us with r cosine squared minus 6 sine. And these are equal to 0. Using our zero product property, we get r equals 0, and we get r cosine squared minus 6 sine equal to 0. So we've got two equations here, right? We got r equals 0, and that is already solved for r. And then this other one, solving for r, we're going to move the sign over and then divide by cosine squared and get r equals 6 sine of theta divided by cosine squared theta. All right, so we have like two answers here, and we really would prefer not to have two answers. So we're going to try to see if r equals 0 lives inside of r equals 6 sine of theta divided by cosine theta. And if we can show that it's part of that, then we don't need the r equals 0 part. The way that we're going to do this is we're going to substitute 0 in for r into this 6 sine over cosine squared equation, and we're going to solve for theta. If we get an answer, then that means that r equals 0 lives inside of this other equation. All right, so 0 equals 6 sine of theta over cosine squared. This is technically a proportion, so I'm going to cross multiply. We get 0 equals 6 sine of theta. Solving for theta, we'll divide by 6. And then we need to use our inverse sine. Theta equals sine inverse of 0. And where is sine equal to 0? Well, that happens at 0 and at pi. So we got an answer. That means we don't need to include this. It's already inside of here. So that's our final answer. All right, let's go the other direction. Here we're given equations in polar coordinates, and we want to transform it to rectangular coordinates. That means we want to get rid of r and theta and be left with x and y instead. Well, I see 4 sine of theta, but that's not one of my formulas. I need r sine of theta to substitute y in, and r by itself, that's not one of the equations we've learned to convert back and forth with either. Our equation has r squared in it. So we want to think about what we could do so that we had r squared on the left side and r sine on the right side. Now, if we multiply both sides of our equation by r, we're going to get r squared equals 4r sine of theta. And now we can substitute in. R squared is equal to x squared plus y squared. And r sine of theta is just y. So we get 4y. This is going to be a circle. I'm fine with this notation. If you want to leave it in general form, I guess for general, technically we should be equal to 0. I'm fine with that. If you really want to complete the square to get it into standard form, that's okay too. But I usually don't do more work unless there's a reason to do that more work. And we know that it's a circle because x and y are both squared and they both have the same coefficient. Next, let's transform the equation theta equals pi over 3 from polar coordinates to rectangular coordinates. In this example, we're going to use the fact that tangent of theta is equal to y over x. We can solve this equation for theta. Theta is going to be equal to tan inverse of y over x. So I'm just going to take that pi over 3 and substitute it in here for theta. So pi over 3 is equal to tan inverse of y over x. Just how tan inverse works, that would mean then that tangent of pi over 3 is equal to y over x. Tangent of pi over 3 is on our unit circle. Tangent of pi over 3 It's square root of 3 over 2 divided by a half to just give us square root of 3 is equal to y over x. And typically when we are in rectangular and everything's linear, we like it to be solved for y. So we'll multiply both sides by x and get y equals the square root of 3x. This is just a line, since everything's linear, a line with a slope of square root of 3.